Hello again. I want to talk today about probabilities, and in particular probability distributions for binomial random variables. And remember that a random variable is binomial if it counts the number of successes in n independent trials where the trials are independent and result in one of two outcomes that we usually call success and failure. And the probability of success we symbolize with a P, and the probability of failure with a Q, and of course P plus Q is always equal to 1 because these are complementary events. So I've started Minitab, and that's on your screen right now. We're going to look at a probability distribution that is binomial, and we're going to work a series of problems out of the textbook that concern ourselves with Gregor Mendel's experiments with P's. And Gregor Mendel was a friar who lived in Czechoslovakia. He was born in 1822. And he died in 1884, and he's called the father of modern genetics. So he noticed that certain P's had traits that seemed to be passed from generation to generation in predictable percentages. Things like yellow pod or green pod, smooth pod or wrinkled pod, and combinations of these. So today we're going to start in our textbook on page 219 and work a small series of problems that all have to do with Gregor Mendel's P's. And so let's look at problem 25, and since you don't have it in front of you, I'll read it quickly. Our textbook, problem 25, says find the probability that at least 2 of the 6 offspring P's have green pods. In our textbook, exercises 25 through 28 all refer to the experiments of Gregor Mendel's in hybridization with P's. The probability of offspring P's having a green pod is 3/4 or 0.75. So this textbook says the display lists the probabilities obtained by entering the values of n equals 6 and p equal 0.75. I'm going to do that for you in Minitab, and then we'll answer these book problems. Problems like 25 says find the probability that at least 2 of the 6 offspring P's have green pods. If at least 2 offspring P's with green pods are required for further experimentation, is it reasonable to expect that at least 2 will be obtained? So let's start hacking away at this. So the first thing we're going to do is to get the probability distribution. Now, from reading the book, we're going to define a random variable that in this particular instance I've called G, and G is going to be the number of green pods in the 6 offspring that we look at. So how many green pods could we have if we look at 6 pea plants? Well, we could have 0 through 6. So let's put those numbers in, not by typing, but by going to the calculate button, make pattern data, simple set of numbers, and we'll fill out the required menu here. Where do we want to store these? We want to store these in the first column, which we call G. From the first value, which would be 0, to the last value, which would be 6, in steps of 1, and just do it once. And so that's all filled out correctly. Boom, we've got our numbers in. Not really necessary for 6, but very handy if we had been looking at 30 plants instead of 6 plants. Now let's get the probabilities. Let's go to Calculate Probability Distributions, Binomial, and fill out a menu. So we were looking for the probabilities, not the cumulative. We'll get the cumulative in a minute. The number of trials, well, here we're just looking at 6 plants, and so the number of trials would be 6. The probability of getting green pods, the textbook tells us, is 0.75. And we're going to do this for all the values the random variable can take. So what we're going to use as the input column the column C1, which we've also called G. And for the optional storage, we're going to store that right next door, and I've already typed a P of G on the column right next door. That is the probability of these values. So that would be optional storage would be, I see it's not quite correct, but we'll make it correct by selection. Now I think everything is ready. You can see an 11 down here, but that's not going to be looked at by Minitab because this radio button, input constant, is not checked. We're going to be looking at an input column because that's the radio button we've selected. Let's say OK, and here are the probabilities then. And while we're here collecting probabilities, it's probably a good idea to go ahead and get the cumulative probabilities. So let's make C3 the cumulative probabilities. Let's label this correctly, and we'll call this the probability that G is less than or equal to the value of the random variable. That the random variable G is less than or equal to one of these values. Okay, now we'll fill this in. And so we go to calculate probability distribution. We're going to calculate a binomial probability distribution. Got to fill out a menu. So we want the cumulative probabilities this time, less than or equal to. Number of trials is 6. The event probability is 0.75. Our input column is column 1, G, so that's filled out correctly. But our optional storage is not P of G. Our optional storage is going to be C3, the probability of being less than or equal to G. So with all those selections, we'll say OK, and now we've got the cumulative probabilities. So this will be for reference as we work problems like problem 25 that I just read to you. Now earlier I copied this information onto my graphics tablet so we can have it here as we write. Let me get the stylus out and remind you the first question we were asked was, this was number 25, and we were said if X is equal to the number of green pods, what's the probability of at least two green? First thing I want to do is to translate that into a statement using X. So that would be what? At least 2 green would be X, the number of green pods, has got to be greater than or equal to 2. Now we could calculate the probability X greater than or equal to 2 by going to the probability column and adding the probability X is equal to 2 to the probability X is equal to 3 to the probability X is equal to 4 and so forth. But you know, that's a clumsy way to do it. But if we'd use the law of complements here, we know this would be 1 minus the probability of the complement. Now if X is not greater than or equal to 2, X must be less than 2. And X is discrete, so X less than 2 means the probability X is less than or equal to 1. Now, I mean, why bother with this step? Well, we bother with this step because the cumulative probability distribution is always giving me less than or equal to, not less than, and there's a difference. So I want less than or equal to if I'm going to use this cumulative probability column, which I think we probably should use. And so this is 1 minus, what's the probability x is less than or equal to 1? Well, we'll find 1 as a value of the random variable g, and this entry would be the probability x is less than or equal to 1. So that looks like it's 0, 0, 4, 6. And so this would be 4, 5, 9, 9. So it's 99% certain that the number of green pods is going to be greater than or equal to 2, as long as this p equal 0.75 is in fact correct. So is it likely? Now, when you read your text, you'll see that it says that the experiment only goes on if we get 2 or more green pods, and then it asks, is it likely that the experiment goes on, which is the same thing as saying, is it likely that x is greater than or equal to 2 or more green pods? And the answer is yes, because I'm going to say yes because the probability x greater than or equal to 2 is greater than 0.05. And 0.05 is the cutoff that we've imposed on the probability of unlikely events. So that worked out okay, not too hard. Let's try problem 26. And in problem 26, the question is, with some verbiage, but it boils down to what's the probability that x is at most 2 green pods, which would be x less than or equal to 2. At most 2 green pods would be x not less than, but less than or equal to 2. And this would be equal to, well, that's an easy one. X less than or equal to 2, I would find 2. And in the cumulative column, I see we've got an 0.376, 0.0376. That's the probability x is less than or equal to 2. And then the second question from this problem, is it unusual that x is as small as 2? And we're going to say yes, because the probability that x is less than or equal to 2 is less than 0.05, which makes x less than or equal to 2 be an unusual event. It has a probability of occurring of less than 5 times out of 100. And 26, actually this was 27, I see now. So all we have to do is change the 6 to a 7. Now let's go back and get 26. And 26 says, what's the probability of at most 5 green pods? Probability of at most 5 green pods. Well, we've got to translate that, and that would translate into the probability of x. Now what does it say? At most 5. At most 5 would be x less than or equal to 5. That is what that would say, isn't it? And at most 5, again, 2 ways we could get that. We could add up I equals 0 to 5, probability x equal x, well, we can just say equals I. That is x equals 0, x equal 1, x equal 2, and we could go to the probability column and we could add up the appropriate entries here, 0, 1, 2, 3, 4 down through 5. But certainly that would not be the easy way to do it. We've already added those up into the cumulative probability column. So less than or equal to 5 would be 0.8220. 0.8220. And we get that just by reading off of less than or equal to 5. And the probability is in the cumulative probability column. So that's what I would use. I wouldn't do it the hard way. Let's go to problem 28. And problem 28 says, what's the probability of 5 or more green pods? The probability x 5 or more, greater than or equal to 5 green pods. Well, the cumulative probability doesn't give me greater than or equal. It gives me less than. So let's use what we know, law of complements, and we know that we could write this as 1 minus the probability that x, what's the complement of x greater than or equal to 5? That would be x less than 5. Now, I don't have a column in my probability table for less than 5. I've got a column for less than or equal to. But in a discrete random variable, if it's less than 5, then the most it could be would be 4. The probability that x is less than 5 is the probability that x is less than or equal to 4, because this is a discrete random variable. And this is equal to 1 minus, and all we have to do is to scroll back up and pick up our probability table. And if we did that, it would be 4, 6, 6, 1. 4, 6, 6, 1. And then it's just subtraction here, 5, 3, 3, 9. Let's double check this. 4, 6, 6, 1 is the probability x is less than or equal to 4. Let's scroll up. 4, 6, 6, and I've rounded that, and that gives me 4, 6, 6, 1. So that's perfectly correct. All right. So that's the answer to problem 28. In problem 33, this doesn't have to do with Gregor Mendel again, but we're given a story which leads us to a random variable x that's binomial, 20, 0.48. Now there is a story that you'll get if you read problem 33, but we can operate without the story for right now. What does this notation mean? It means that it's binomial on 20 trials, and so those would be independent trials. We're repeating a basic trial operation 20 times, and the probability of success is 0.48. So on each of these 20 trials, there are only 2 outcomes, success or failure, and the probability of success is 0.48. And the first question, without really knowing why they want us to calculate this, the first question is, what's the probability x is equal to 12? So what's the probability x is equal to 12? Well, actually, for the binomial random variable, we have a probability function, and if we know the distribution of x, we can calculate probabilities. So for x equal to 12, where x is binomial 24, 8, this would be 20, choose 12, 0.48 to the 12, 0.52 to the 8. Now, let's look at why all those. Because we want 12 successes out of 20, and the number of ways we can pick the trials that are successful would be 20 choose 12. So each of those 20 choose 12 outcomes would give me an x that's equal to 12, and each would have a probability of 12 successes. That would be 0.48 to the 12th. You'd multiply those because they're independent, and then 0.52 everywhere else. Well, there are 20 trials, and so if I've got 12 of them here, successes, then the rest, or 8, have to be failures with a probability of 0.52. So that makes good sense, and that's a quick way to calculate the probability of an individual outcome when we're dealing with a binomial. But Minitab will do that for us also. So I want to just show you how to do that in Minitab. So let's go to calculate probability distributions and a binomial. So far we've done all this before, and we've seen this menu before. Now we want equal 12, and so we want a probability, and the number of trials is not 6, but the number of trials in this problem is 20, and the probability of success is 0.48 in this problem. And I'm not going to use an input column. I just want one value, so I don't need the whole distribution. I just want to know about the input constant 12. So I'm not using input column, I'm using an input constant. Now I could store that somewhere if I wanted to, like I could store it in C4 or C5 or C6, but if I don't pick storage, it's going to give me the result up here in my operations part of the screen. So let's just say OK right now, and Minitab responds with that we're calculating a binomial with n equal to 20 and p equal to 0.48, and the probability that the random variable x is equal to x, but this says our x is 12. That probability is 1,00737. So I don't have to have the whole probability distribution if all I want is 1 point. Now, there's a next part of this question on 33. It says, would 12, I guess we'll go back here. Would 12 would x equal to 12 be unusually large? Well, we answer that by calculating the probability that x is greater than or equal to 12. If this probability is less than 0.05, we'd say, yeah, that's unusual. But if this probability is greater than 0.05, we'd say, no, it's just kind of run-of-the-mill, happens every once in a while. Now, how are we going to calculate the probability that x is greater than or equal to 12? Well, we could do it by hand, but if we're going to use a cumulative probability, the cumulative probability is not greater than or equal to, it's less than or equal to. So I could write that this is equal to 1 minus the probability that x is, now what's the complement of greater than or equal to 12? The complement would be less than 12. But x is a discrete random variable, so I would write that this is 1 minus the probability that x is less than or equal to 11 is equal to, now let's go back to Minitab, and let's ask Minitab to calculate for us probability distributions, binomials, and I want the probability that x is less than or equal to, that's going to be a cumulative probability, less than or equal to 11. Now let's just double check that we've got everything else right. We've got a cumulative probability, number of trials is 20, probability of success is 0.48, and we're using an input constant of 11, and we don't ask for storage, and so I think if we just say OK, here we get the probability that x is less than or equal to 11, and that probability is 0.8024, rounding to 4 decimal places, 0.8024. So let's go back to our graphics tablet. 1 minus 0.8024 is equal to 1976.1976, and I see this is quite a bit greater than 0.05, and so we would say it's not unusual. It happens on a pretty regular basis. Now this has already got a little bit longer than I'd intended, but the next problem I think is just interesting. I've liked this problem since the first time I read it. So we're going to work problem 38 out of this section, and then we'll quit. And problem 38 says that in the airline industry, sometimes people buy tickets, but they don't show up. So the probability of a no-show according to this problem in our textbook is 0.995. The probability of a no-show is 0.995. That seems kind of high, doesn't it? But if you sell every seat on the airplane, then you're probably going to be flying with almost 10% empty seats, because 0.995, that's about 10%. About 10% of the people don't show up. Well, if you're an airline, you want to fly with all the seats filled because that's how you maximize profit. So what you might do is oversell your flights. You might try to sell maybe 10% more than what the capacity of the airplane is, thinking that about 10% won't show. So that would maximize your revenue, wouldn't it? That seems like maybe kind of a good idea. Or maybe not. So they name a particular aircraft. It's one of the small ones. I think it was a Beechcraft. And it seats 19 persons. Should we sell 21 tickets, thinking that 19 or less will show up? If we sell 21, maybe 19 or less will show up, in which case we win. Of course, if more than 19 show up, not so good. Not so good. Now, if we let X equal the number who show up to take their seats, then X is, let's think through what X is. We sold 21 tickets, and so we're talking about the behavior of 21 different people, and they make a decision whether to show up or not. And so X would be calculated from 21 trials. Are they independent? Maybe not exactly. Why? Because some of these 21 people are going to be husband and wife. And if one doesn't show, then more than likely the other won't show. Why would a husband and wife not show? Oh, a sick child, or mad at grandma right now and don't want to go see her. So, not quite independent, but probably close enough to independent that we can just make the assumption. So we would make that assumption, and it looks like X is based on 21 independent trials. Each trial has two outcomes, show up or don't. And X counts the number who, what do we want? The number who show up is what we decided we'd count. Now, what's the probability of show up? Well, I know the probability of a no-show is 0.995. So that would be over here, 0.0995. And that's the number we've called Q. But the number we call P would be the complement. And so P would be 0.9005. So this would be the probability that somebody shows. There's a 90% probability that they show. Now, when is the airline in trouble? Well, it's going to be a bad outcome for both the airline and for the purpose of the person that holds a ticket if X is greater than 19. If we get the number who show greater than 19, I don't have seats for everybody, so somebody's going to be disappointed. So we want to know if this is a good idea. I don't know a better way to decide if it's a good idea than by seeing how often this is going to happen. That is, what's the probability that X is greater than 19? Well, it's cumbersome to calculate greater than 19, but it's easy to calculate the probability that X, now what's the complement of greater than 19? Less than or equal to 19? So what's the probability that X is greater than 19 is 1 minus the probability X is less than or equal to 19 is 1 minus, now we can go to Minitab and we can calculate the probability X is less than or equal to 19. Before we go, let's remember that X is binomial, N is 21, and P is 0.9005. So we're going to need that information. And let's just zip over to Minitab, and we want to calculate a probability distribution that is a binomial, and we want the cumulative, and the number of trials is 21, and the probability of success is 0.9005, and we're going to use an input constant of 19, and this will calculate the probability that our random variable X is less than or equal to 19, and that's what we said we wanted. So the probability that this X, binomial, N equal 21, P equal 0.9, the probability that we're less than or equal to 19 is 0.6324. 0.6324. Let's take that knowledge back to the graphics tablet. 0.6324 is equal to 0.3676. So I would say this is really not a good idea, because you're going to have unhappy passengers. Let's call this, is overbooked the right word? I oversold the seats. Let's just say too many passengers (37% of the time). And that's got to be a bad business model. All right, that's all that I wanted to do. I just wanted to work some problems with you using the binomial random variable and going over Minitab a little bit again. So that's all for right now. You have a really good rest of the day whenever you're watching. Goodbye.